Okay, welcome everyone. Thank you for joining. I'll just start out by saying welcome to everyone. This is GL's webinar for March 2018. We try to do one of these webinars every month with different topics and different areas of GL's test solutions and so forth. So this webinar, we're in the air traffic management industry today, and we're talking about ED-137 test solutions. So this is new voice over IP related protocol for the air traffic management industry. My name is Matt Yost. I'm joined by colleagues Srinivas and Sanjeev. This webinar actually follows a recent visit that GL had to Madrid, Spain, where we participated and had a booth at the World ATM Congress show. So if we met you there, myself and Srinivas were there along with our sales director Shelly Sharma. If we met you there, thank you for meeting with us, and we enjoyed our visit there, and we're glad to have you today for our webinar. So we'll say this on just an administrative note. As we go through this webinar, there's a lot of material to cover, and we're going to be highlighting our test solutions in the air traffic management world. Please note your comments or questions for us, and you can actually type those into the GoToWebinar toolbar there, and we're going to be monitoring them throughout the webinar. And we're going to have time at the end where we can have a discussion. You can ask your questions, we will address them, and we'll take as much time as needed to answer all of those and to talk to you about things. So just note your questions throughout the webinar, and then we'll take some time to address them at the end. One other note on that is we're going to be recording the webinar. So at the end of this, in a day or so, we will post the recording on our website at gl.com. So I encourage you to go back and grab that, take a look at it, study it a little bit more, maybe send it to colleagues and so forth from your engineering team and so forth, so that they can take a look at it and understand what solutions we have. So let's go ahead and get started here, 4 after the hour. So let's go ahead and get started. GL Communications, if you're not aware of us, we are located in the United States in Gaithersburg, Maryland. So we were founded in 1986, and again, we're located in Gaithersburg, Maryland, which is right outside of Washington, D.C. We have offices in Bangalore, India, and Shanghai, China, and we have representatives around the world in a lot of different countries to help and support our products. So we've done, over the years, and we still do engineering consulting services, but our main focus is on test and measurement equipment. So for 30+ years, GL has been in the telecom testing arena. So we've been manufacturing hardware and software testing products for telecom companies throughout the world. So we're not new to test equipment by any means. We've been in telecom testing for a very long time. It was a natural move for GL to get into the air traffic management industry, especially with the introduction of ED-137 and voice over IP. So with that, we have a lot to cover today. I'm just going to go ahead and move forward. Today's agenda, we're going to start out with, if you're familiar with our emulators, we call them. So we have an ED-137 radio emulator, which focuses on air-to-ground sessions and PTT enables, squelch break type sessions. We have a telephone emulator, which is a ground-to-ground emulator. These guys emulate the ED-137 protocol. We can get into more detail when we get into the slides, in a single call, single session manner, as well as in a bulk calling manner. We also have now, which is a fairly new product of ours, the ED-137 Recorder. So the Recorder, Srinivas will get into how we've tackled that, but we have this Recorder option now on our emulators that's very similar to how we've done radio and telephone, so you'll see that. We'll touch a little bit on our packet scan product and NetSurvey Web products, those are monitoring solutions. So these are non-intrusive monitoring solutions, and they focus on ED-138 type calling metrics, quality of service, packet loss, jitter, mean opinion score, MOS scoring. So all of that is in that packet scan and NetSurvey Web offering. And then finally at the end we'll get into another area that we have ported over some of our test equipment, and that is critical delay measurements. So we have the ability to do some very precise delay measurements within the network, and we'll show you how we do that and how we're tackling that. So with that said, I'm going to go ahead and hand this over to my colleague Srinivas, who will be taking over and talking first about our emulators.
ATM network with basic components. Here we are trying to show where our test solutions fit in this typical ATC network. We can simulate the controller working positions, voice communication system, a ground radio station, or a recorder. And we can also capture all the traffic in the ATC network non-intrusively and provide real-time and historical analysis with voice quality metrics such as MOS, packet loss, latency, and jitter. So we cover almost all aspects of testing ATM networks as per ED-137 specifications. So now we'll begin with our emulators for radio, telephone, and recorder interfaces. MAPS is our common framework used to simulate all products across domains such as TDM, IP, and wireless. MAPS stands for Message Automation and Protocol Simulation. As the name indicates, the framework provides ability to customize messages and protocol call scenarios. It's basically a script-based product. So now we'll begin with the first emulator, that is MAPS ED-137 telephone emulator. It's a lightweight software-only product. It can run on any computer with Windows 7 and above. It comes with easy-to-use graphical interface, and it also provides a CLI API access for seamless integration with third-party test solutions. This image shows a typical or a simple ground-to-ground call setup here. We are emulating CWP as a ED-137 telephone emulator, and here you can see a real CWP. Which can be tested using our emulator here. Okay. Yeah, we can simulate multiple CWPs, each with unique IP addresses in a single instance of MAPS. It also supports codecs such as ELA, ULA, and G729. We can perform traffic actions such as send and record audio files, send and detect digits and tones, and talk using microphone and play to speaker. It also supports all the call services like call hold, call transfer, and etc. And we can also simulate forceful rejection of call using the SIP errors like 4xx, 5xx, and 6xx. And we can also generate bulk calls to perform the load testing of the device or the network under test. So these are the 8 telephony call types defined by the specification, and we support all of these things. And along with this, we also provide the call graph and message decodes for the detailed analysis of these calls for each and every call that we are generating. Yeah, next one is a MAPS ED-137 radio emulator. It's again it comes with the same specifications as telephony. Yeah, in this image we are trying to show a simple A to ground call with MAPS ED-137 radio emulating as either a CWP or the GRS, and it supports both ED-137 1P and C standards. Usually user will have an option to select the standard and node to be emulated when product is invoked. It also simulates multiple CWPs and ground radio stations in a single instance of MAPS. It supports all the radio call types, PTT types, and SIP and SDP headers. And it also supports the radio features such as link session management, WG67 key in event, call preemption, and PTT priority handling. Now continuing with the MAPS ED-137 radio features, in this screen we are showing how multiple radios can be configured. Each profile represents a radio and it will have its own set of parameters like radio emulation type, frequency ID, maximum number of calls supported. It supports all the 4 RTP header extensions defined by the specifications. Basically, they are like climax time delay, signal quality index, radio remote control, and dynamic delay compensation. And we can also set the DSCP values, that is differentiated service code point values, which will be assigned to the packets to prioritize the packets in the network. And we can also introduce impairments such as latency, packet loss, and packet effects such as duplicate packets and out of sequence to simulate a degraded network. Yeah, this screen shows a AZ calls to multiple radios. We are using unique color codes to identify the calls to a particular radio, and we are also grouping them together. And you can see here, this is the script zip call control which is used to simulate an AZ call. And this is the radio and the controller involved in this call. And you can see here the call status will be updated as and when the call progresses. And this is the squelch button. At the CWP will be having a PTT button to apply a PTT or the squelch. And each of these scripts can result into a pass or failure as defined by the user in the scripts. And we also have a another set of events here. Okay, so these are basically like applying signal quality index, or we can apply the SCT, we can turn on the SCT bit, PTTS bit, or we can apply the impairments. So these events can be applied on each of the sessions. And below here we are showing the call graph of the selected call here, along with all the events and the timestamps, and also the message decodes. We also provide automated scripts to perform PTT and squelch operations periodically or randomly. And we also detect and count the synchronous transmissions, which will be happening due to either pilot transmissions or controller pilot transmissions. So this one parameter, it helps to study the traffic congestion in the busy airports. And in this screen, we are trying to show how we can simulate multiple controllers and the radios. And using these multiple controllers and radios, we can generate hundreds of simultaneous A to ground calls. So the next slide lists out all the ED-137C features that we have supported. So basically important ones are radio receiver multicast operation. This one actually, it helps to maintain a single stream at the radio and put all the overhead of multicasting these RTP and R2S packets from radio towards the all the connected controllers on the multicast router. So by that way, it will also reduce the bandwidth and the burden in maintaining multiple sessions at the radio. And the second one is a SELCAL tone transmission. So it basically, in this case, the controller sends a 4-digit code using the SIP info message before activating PTT to a particular aircraft, which is identified by that code. So basically the ground radio station, after receiving this code, it will generate an analog tone towards the aircraft to indicate the PTT activation. So apart from that, there are other features like they have added the test PTT simulation, and there are some reservations of the PTT IDs assigned to a particular feature. Now, next one is a MAPS ED-137 Recorder Emulator. It is a new addition to our ATM test solutions. Okay, and it has a similar specification as we have seen in radio and telephone emulators. So this image shows the recorder interface being emulated by MAPS ED-137 recorder at different nodes like controller working position or a VCS, and at the ground radio stations, and also at the recorder. So these are the interfaces that we are trying to emulate using this recorder emulator. Basically, these are like RTSP sessions towards the recorder from either CWP, GRS, or the VCS. Again, we can simulate a recorder interface from multiple CWPs and radios. And it supports the recorder emulation as per the ED-137 volume 4B, which is for recorder emulation. It can simulate both air to ground and ground to ground recording sessions, and it also, the supported codecs include like ALAW, ULAW, and G729. So this slide shows the common use cases for recorder emulator. In the first case, recorder vendors can use our MAPS tools to simulate the air to ground recording sessions towards the recorder to test the recorder interface within this recorder. Similarly, they can use to simulate this ground to ground recording towards the recorder interface. And in the next slide, this can be like this is for the CWP and VCS vendors, wherein they want to test their recorder interface within their entity. So we can simulate the recorder to test their recorder interface. Similarly, the GRS vendors can also use it in the same fashion. So this slide shows profile parameters for recorder interface at CWP. So you can see here we are configuring all the RTSP IP address, the recorder address, and other informations used to emulate an A to ground or a ground to ground recording sessions. We can easily define the custom call record data properties and operations. And recorder node records voice on each session to audio files, and it can also store the call record data to CSV format. And we also provide scripts that allow to perform PTT and squelch operations on the sessions periodically or randomly. And whenever we perform the PTT or a squelch is triggered on these RTSP sessions, we can either send a pre-recorded voice files to achieve the automation, or we can talk using the microphone when we are doing the manual testing. So this slide shows the way to make the RTSP sessions to the recorder. So this is the script here, RTSP call control. Okay, and this session is between this controller 1 to the recorder at IP address 1.59. So we have provided the option events like PTT and key PTT and unkey PTT buttons here, and these scripts can result into pass or failure, that those as defined in the scripts. So it will be notified here, and we can also run these scripts repeatedly for multiple iterations as defined by the user, and it will show the current status, like how many iterations are completed and all. And below we are showing this RTSP session call graph here along with the timestamps, and there is a message decode here. And we can run multiple scripts, configure them to run simultaneously or sequentially or randomly. We have these options for automation also. And we also have a test scheduler that will help to run multiple scripts at different intervals as defined by the user. And we can generate hundreds of RTSP sessions towards the recorder to perform the load testing on the device or the device under test. So in reality, recorders need to be recording hundreds of calls all the 24/7. So it becomes inevitable or a mandatory that they pass through this scenario before deploying them into the actual network. So Maps helps in creating all these scenarios to do all the deployment test and all the functionality tests. So that is actually all about our emulators. Now we'll move on to the monitoring solutions. So these monitoring.
Let me interrupt you just 1 second. Could you do me a quick favor, because I wasn't quite understanding. Can you go back to slides 17 and 18 real quick and explain again the different cases that the recorder that we have now can emulate, and sort of the differences in these?
Yeah, say for example, there is a recorder vendor and he wants to do the testing of this recorder. So basically, we can emulate the recorder interface at the CWP point or at the GRS point. So CWP and GRS are involved to create this A to ground call recording. Okay, as I told, we can create multiple controllers and multiple ground radio stations, and between these things we may be having hundreds of A to ground calls. So all those calls need to be recorded by creating sessions to the recorder. So either they can also perform the functionality test by doing one single sessions, or they can generate a bulk sessions to perform the load testing. So in this second case, it is something like here we are trying to simulate the ground-to-ground call recording towards the recorder. So all the other aspects will remain same. The only difference is in the first case we are trying to emulate the A to ground call recording. In the second case we are trying to emulate the ground-to-ground call recording.
So in these two scenarios, the recorder is already manufacturer's equipment, and the Maps is actually trying to test the recorder at that point. So the deployed recorder and so forth. Is that right?
Yes, that is correct. And we are emulating only this RTSP, I mean the recorder interface, which includes this RTSP sessions and RTP for the media.
Okay.
So in the next slide, it could be like the controller working position or a VCS vendors, and each of these entities will also have a recorder interface. So they may want to test it against the recorder by by making the RTSP sessions to the recorder whenever there is an A to ground or a ground to ground call. So in that case, Maps can act as a recorder itself, where it will be trying to receive the RTSP sessions, and it will record all the voice that is coming in, and it will also store the call record details to the CSV files, so that later users can verify these things. And similarly, this GRS, ground radio station, involved in A to ground call recording.
Okay, yep, that's clear now. Thank you.
Okay, thanks. So now we'll move to the monitoring solutions. Okay, so basically we have two monitoring solutions, Packet Scan and NetSurvey Weblight, that work hand in hand to provide real-time and offline analysis of ATM network. So this image shows a simple ATC network where we have all the A to ground and ground to ground calls happening. So packets can capture all this traffic in this network non-intrusively through a switch with the mirror port here. Okay, it can process the frames, measure voice quality statistics on all the calls, and send call detail records to a database server. So later we have a web-based application, that is NetSurvey Web, which can query to this database and display all the call detail records and also the report, both real-time and historical analysis. So our first monitoring solution is this packet scan. It's a lightweight software only product, and it has a very user-friendly graphical interface, and it again runs on the Microsoft Windows platform. Basically, it is used to evaluate the overall network health or to solve deep protocol issues. And it can capture the traffic in real time, or it can also be used to process the offline traces also. So basically, it offers a powerful feature to capture and monitor A to ground and ground to ground calls in the network. You can see here it provides the call frame summary and frame decodes for all the frames that it has captured, and it decodes SIP RTP and all RTP header extensions as per this ED-137 specifications, and it provides capture and view filters to analyze only the traffic of interest. It can also import and export the Wireshark traces. Yeah, in the next slide, this is the packet scan call summary view. And here we are displaying all the calls in the network along with the complete call detail records. It provides ED-130 defined voice quality statistics such as MOS, latency, jitter, and packet loss. So you can see here each of these one is a signaling details here, and the other two sessions are something like a PTT session and SQL session, or the two sides of a call actually. So we can see here some of the calls have a very good MOS score, that is 4.2 without any degradation, but few of the calls have a degraded MOS scores, and we can also get the reason for that degradation. We can see here missing packets. Okay. So similarly, it gives complete details. We can see here average gap, average delay, jitter. These are the important quality metrics as defined by the ED-138. So along with this, it also provides the counters for PTT squelch, PTT summation, PTT mute, and also the SCT counters due to pilot or the controller pilot transmissions. So yeah, and again it provides the call graph and the message decodes, and we can also record and playback the voice on the call, and we can detect the digits and tones on the call, and it also provides the graphical analysis of the call such as call graph, MOS, jitter, and latency variation graphs. And we have a feature called triggers and actions also, which will allow to define thresholds or the filters for the calls, and it can perform certain actions on the filtered calls. For example, I can define filter to filter calls with low MOS scores, and send email notifications, and whenever those kind of calls are filtered, we can send email notification with audio and trace for that call. So next one is a NetSurvey Weblight. It's a web-based network surveillance system for air traffic monitoring. It can work with multiple probes to non-intrusively monitor at remote locations, and it has a scalable and flexible architecture to define custom filters and reports, or the KPIs, key performance indices, which will give a clear picture of the health status of the network. It can show the real-time and historical data, and it also supports multiple users. And you can see here, this is the call detail record view, where the captured calls are displayed here, and I have expanded a couple of these calls, which indicates the payload, total packets, and all other voice quality statistics. And we have defined some quick CDRs also to quickly look at the A to ground calls or the ground to ground calls, and also poor MOS calls or the failed calls. Yeah, this view shows the detailed view of a particular selected call. So you can see here we are listing out all the events like PTT and squelch that have happened on the call along with the timestamp details, and also giving details like what is the PTT type, PTT ID, and we are also measuring the MOS scores and all the voice quality statistics for each individual PTT and the squelch transactions. And in the below also same thing is represented using the call graph, and we get all the message decodes here. So next one is about the reports and graphs generated. So we have a default reports for the ED-137 this one. So here we are defining the conversational MOS graph and packet loss graph, or the SET counters, which include both pilot and controller pilot induced SETs. And it also gives the failure calls with different reasons listed here. Okay. So basically, we are providing some reports, the valuable reports as a default, but user has a complete flexibility to define his own reports or the key performance indices here. He can define the filters, he can define the reports, and he can select the time duration from when and when he wants to analyze. So it gives the complete granular details about the complete network under monitor. And last one is about the triggers and actions. So similar to packet scan, the packet scan web also provides the triggers and actions features. So here the main difference between packet scan and NetSurvey web is like packet scan is instantaneous things, like it processes the calls, it sends all the details to the CDR, and then it's done. It cannot show the historical data. Okay, but since NetSurvey web is querying to the database, which has a data for a very long period, so it can query and get the details. So we can get the notifications like email, log event, or visual and audible alarms. We can also generate daily, weekly, and monthly reports through email. So this covers our all the emulators and monitoring solutions. Now I will hand over to Matt for next slide's presentation.
Okay, thank you, Srinivas. Sanjeev, do you want to take a quick break to address a question or two before we get started on the last portion?
Yeah, we have a couple of questions. The first question is for MAPS ED-137 radio, what is the maximum number of simultaneous simulated endpoints?
It basically, like, we can go up to a couple of hundred nodes can be simulated in a single instance of software. For example, we can simulate 200 CWPs simultaneously.
Okay, and are there like separate IP addresses required? For example, if for 200 IP addresses, do we need to have 200 simultaneous sessions to be simulated?
In case of if you are trying to emulate multiple radios, we need unique IP addresses. But in case of when we are emulating controller working positions, you may or may not prefer that option. So basically, so yes, we do need unique IP addresses. So we usually we do create them automatically whenever we configure the profiles. So user need not bother about configuring them separately.
Okay, so the software does take care of the multiple IP addresses, is what you're saying, both on
Yes.
the CWP side and on the GRS side.
Yes. So in the profile, we provide the option to configure the subnet mask and the IP address range from where and where we want to simulate, kind of thing. So based upon that, we'll automatically create those IP addresses on the system or the available link.
Okay.
Okay. Next question is, can CWP and GRS emulation be performed simultaneously?
Yeah, you see the maps. It can maps radio. It can act either as a CWP or GRS. So this needs to be configured when we invoke the node actually. Okay, but if you have a two maps instances, then obviously you can make calls between them. So that will simulate the A to ground calls between those two instances. But a
Okay.
single instance cannot emulate both CWP and GRS simultaneously.
One last question we can take. Which protocols are supported for ED-137 recording? Unicast, Multicast, TCP, UDP?
Yeah, I mean, right now we have supported TCP for audio transmission, and we do have plans for supporting UDP and interleaved RTSP also. So those are going to happen very shortly.
Fine. We'll take up the next questions at the end. Matt, you can continue.
Okay, yeah, thank you. Let me introduce the next section. It's a few slides here. What we're going to talk about is critical time delay measurements. When we're talking about critical time delay measurements, you know, first thing that comes to mind is who this is important to. And we have noticed that ANSPs, so service providers, are very interested in this area of our test solutions. And they need to know basically the manufacturer's equipment that they're purchasing and that they're thinking about purchasing for their deployments, are they performing well, you know, from a delay perspective. So these products that I'm going to show you in the next few slides can actually help verify that. So delay from point A to point B within the network, you can surround different products, different nodes in the network, and make sure that the delay through the product is meeting a specification that you may have as an ANSP. So that's one area that we found a lot of interest with these time delay measurements. The other area is obviously within the equipment manufacturer, so VCS guys and creating CWPs and making sure that their processing within their CWPs is adequate. From a time perspective, as well as radio people. So we've noticed that this is catching, you know, it's getting good reviews in the market because it's very precise and it can do a repeatable test to verify delay within the network. So I'll just start out by showing a very simple diagram here of a ATM network. On the left-hand side, you'll see that a legacy VCS is being represented. You have a controller represented on the far left. The legacy VCS will connect via to the network via a VoIP gateway, and then now we've got ED-137 presumably in this arena. Now on the far right, or this portion of the network, on the far right we have a VoIP VCS. So direct ED-137 to the VCS and then an additional CWP. So we're showing a legacy deployment with a VoIP interface, a VoIP gateway interface, and then a purely ED-137 VoIP VCS deployment. On the top side of the diagram, we're showing a ground radio station. Now, we did not break it out, but you can also imagine that one option would be a pure ED-137 directly into the radio, pure VoIP directly into the radio, or via a gateway. Okay, we'll call it. So sort of a legacy from the gateway downstream to the radio. Now, where the timing measurements become important are throughout the network, of course. And what GL has done is brought over some products that we've had for years in telecom testing to put into this ATM world where we can measure delay. So you may want to measure delay in two different areas. That's kind of how we break it out, sort of in the analog world and in the IP world. So different points within your network become important there. So at this point, we're talking purely analog. Even here, it's an analog connection to some extent. After it goes through the gateway, it's an IP connection. So now we're talking Ethernet IP with ED-137. All of this is being represented by IP as well. But after the VoIP VCS, it obviously will go back before the controller hears it to an analog world. So we've got products that can sit now at different locations here. These two products mainly focus around two products. One of them is called the Audio Analyzer. So the Audio Analyzer is a product that can interface in the analog world, as you can see. And then we've got another product called a Packet Analyzer, which is able to monitor in the IP world, in the Ethernet world. And we'll show you a little bit more about each one of those at a high level. But both of these products are sort of the building blocks to allowing us to do measurements from T0 over to T2, from T0 to T3, wherever you want to go to and from, we're able to do that, and we can show you. So you can isolate, for instance, in this situation, you can isolate from T3 to T4. You can isolate the VoIP VCS to see the processing time that it takes for instance, let's say a PTT to be enabled on the analog side to when the PTT bit in the ED-137 protocol is enabled. So that can be timed very precisely, very repeatably with our product. So you could do that 100 times, 1,000 times, just to see how this VoIP VCS is performing. Okay, and you can get the picture on how you can do that from different points within this network. So I will tell you this as we move forward here a little bit. I'm going to one slide will be devoted to the Audio Analyzer, which will be first, and then I'll devote another slide or two to the Packet Analyzer. The event data logger, we're showing it here, the guy that we use to pull in all of these times and to a common platform, and then that's sort of the timer in a sense. So it has the master clock for all of this. We'll show you that. So the Audio Analyzer. This Audio Analyzer, again, in the analog world, can emulate a controller. So it has the ability through this interface right here to connect to your, what we call a dual jack module on a CWP, and it can, through software, can enable and disable PTT at the CWP, and it can send and receive audio. So it's emulating a controller in a sense, in an automated fashion. So through software, and this hardware can emulate a controller. When those events happen, so when PTT is enabled, when PTT is disabled, when audio is being sent, when audio has been detected, we can send a TTL trigger out to an oscilloscope, maybe in a lab where you want to see what time that actually happened, or to that event data logger that we're showing in the previous slide, where we can time it and do a time delta between maybe this interface and an IP interface. So that's what this product does. It interfaces again at the analog side, so it will emulate a CWP, and it can inject and record analog signals at that CWP. It also, in an ancillary fashion, has the ability to send and record voice, of course, as I mentioned, and it can perform voice quality measurements. So you can send from one point in the network to the far CWP and test the voice quality across the entire network. It's been set up as well to play very nicely in an automation environment. So you can talk to this thing through a CLI or an API, and you can integrate it in with third-party test tools. We've actually done that to some extent with the event data logger, because we're talking to all of these guys and at some interface getting the time. Okay. So what I'll say about the Packet Analyzer, okay, now this is the product, this is the hardware product that is interfacing at the IP interface. So it's basically taking packets in and passing them through the device through these things we call the span ports. So it's passing audio and IP packets in one port and out the other. I have a demo of that here just in the next slide, which will show it a little bit better. But as those packets flow through the device, it has a filter, and a filter can be defined to pick off a packet of interest. So when I mentioned earlier about the PTT bit in the RTP packet going high and high or low, we can be looking for those things as the RTP packets flow through. And when they happen, we have the ability to time it. So you can see that these very precise events in the RTP and the IP world can be looked for through our filter mechanism and then triggered. And again, the time is the critical thing there, and we have that. So we can filter at layer 2, layer 3, and layer 4. Again, automation is been built into this product through a CLI and an API. Okay, so we have that. What I'll show you here is how that packet analyzer works from the filter perspective. It's a very simple demo with some automation, but it shows that as packets flow through the device, okay, we use port 2 and port 3 as sort of what we call our span ports. So as network A is pushing packets over to network B, we're running it through our device, and as those packets flow through, we've got our filter defined. Okay, and when that filter sees something of interest that you have defined, again in the example I mentioned where the PTT bit goes high, we can push those packets on over and then downstream to our timer, okay, our event data logger. And so there's a built-in filtering mechanism here, and that's how we're doing things. We're passing all traffic through our span ports, and we're filtering out our packets of interest, whatever may be defined there, and whatever the test calls for, and we're sending those out to our event data logger where the timing is being tagged, and again, that's where the timing is, and that's where you can delta the times within your network. So to summarize that, going back to this diagram, from different points within your network via analog interface at a CWP, we can get a very precise time of when events happen. So as mentioned, these events can be defined by the user, audio coming on and off when a controller maybe mutes the when he mutes the CWP, he or she mutes the CWP, we can be timing that type of thing. When the audio starts and stops, when you mute and unmute, we can look for those types of things. We can look for different events throughout this network. There's many to choose from, and we can do that. So that's the summary of how we're doing our critical time delay measurements. I think at this point we can open up the floor to questions, and Srinivas and myself can help you with those. One thing that I will mention here on the last slide is, as we finish up, just before the questions come in, our next webinar in April will be focused on something, again, that is probably relevant to the air traffic control industry, and that is voice quality, of course. So we've got a whole slew of voice quality testing products that GL offers, some of which we mentioned in this webinar. We're going to be focusing on one of those new products that's coming to market, which we're calling our V-Mobile product. So that's a voice quality testing product that we have that's similar to a few products that we already have on the market, but this one is a truly portable piece of test equipment that a technician can take here and there, and very lightweight in the way that the technician would have to carry equipment. So voice quality testing webinar will be coming up in April, so look forward to that. With that, let's open it up, Sanjeev, to any questions that somebody may have.
Yeah, one question is, which ways are available to remotely control the maps? example the CWP, through external test applications, which API is available?
Yeah, we have a TCL client and a Python client and a Java client. So we have these options here.
And next is for calculation of jitter in packet scan or net surveyor, how accurate are the calculations? Is there a defined margin of error once packets are received from the mirror port?
Since the products are on the Windows platform, it is very difficult to get the precise measurements, but we are getting it up to like 1 millisecond, whatever the timestamp that interface is putting. So based upon that, we are calculating those statistics.
We have one more query related to the audio and packet analyzer. For each T0 to T5 points, do they require 4 audio analyzers and 3 packet analyzers?
So back here, for each, no, not necessarily. I mean, depending on how your test setup and your test lab is configured, these things can be moved around to handle a particular test. If you want it to be a permanent setup, yeah, you would need to have an audio analyzer at different locations. If you wanted them both to be operating in sort of a simultaneous fashion, then the answer would be yes. If your test lab is dynamic and you want to move equipment from place to place, then you wouldn't need to do that. So I think it would depend on how you want to set up your test lab to evaluate these things. The packet analyzer is a little bit probably more, it's easier. It can sit in the IP network. So where do you place it in the IP network? It's sort of a strategic decision on where you place it before, after certain nodes. You can get a little bit clever with how you present packets to it, and you may get away with not having to buy many different ones or multiple of them. You can reuse that. So I mean, to answer that question, it's a little bit tricky to answer just based on not knowing how you want to set up your lab or set up your test bed.
Yeah, we have another question. Does the event data logger have any geographical limitations? In other words, how do you deal with CWPs and GRSs that are in a different areas of country? Is a common time source enough?
So the way we're dealing with that, Srinivas, maybe you can help a little bit with that, but we are packetizing this the event of interest and sending that across and to the event data logger. So typically what we've seen so far is that's been fairly local, a local transmission. So packet analyzer, audio analyzer being locally geographically in a local situation, the event data logger being there as well. If something was located separately, I think we'd have to account for that and see sort of how that plays in, and because the time actually does get introduced, time 0, time 1 is all done down at the event data logger location. So at present, we've done everything in a local manner, local area network. If you had something other than that, I think we'd have to talk to you and analyze that a little bit. Yeah.
Sorry.
Okay, that's fine. The last question would be, do you have any plans to support C version of recorder interface?
Yes, we do have plans, and the specifications are still in a draft version. So as soon as they are released, so we are going to work on that one, and we are going to constantly upgrade our products as per the standards released by EROCAT.
We are done with the questions. If anybody has any more questions, they can send it to info@gl.com and we'll address them.
And then keep an eye on our website, because we will have this webinar uploaded and available to you here in a day or so. But other than that, thank you for your time, everyone. Thanks, Srinivas. Thank you, Sanjeev.
Yeah.
Thank everybody for attending, and we will see you next month. Thank you.
Yeah.
Thanks.
Thank you, everybody.